Okay. So scientific notation is one of those things that to do it, the mechanics of actually like taking a number and putting it into scientific notation are really easy. And I think I almost don't even really need to bore you guys with the details. But what often goes missing in the way scientific notation and significant figures are taught is kind of what's the point of it. And often I think the point of it is kind of the reason you get given for using scientific notation is actually, I think, wrong. So I want to give you my reason why you would want to use scientific notation, and maybe you can agree with me or disagree with me. So the typical reason you get given is that, why is this like this? Anyway, the typical reasons you get given for using scientific notation is basically the idea that, oh, we need it to express really, really big numbers like space, or really, really small numbers like the size of an atom. And it's convenient to blah, 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 blah. And you go on and on about that. And at this point, I have to, by contractual obligation, show you a picture of space and a picture of an atom. And sometimes there's a rocket as well. But I don't think that's actually the reason we use scientific notation, because we have big units and small units. So we can say that an atom is 14 nanometers wide. That's perfectly fine. We don't need scientific notation for that. We can also say a galaxy is 42 parsecs wide. Now, you guys might not know what a parsec is. Oh God, can I remember? It's the angle traced out by something. Anyway, it's a long distance. So, and if we didn't have a unit big enough or small enough, we could just invent one. We could call it, we could say the size of the Milky Way, let's call that 1 Milky, and we could say this galaxy is 5 Milkies wide. And that would be absolutely fine. Oh, thank you, Sabir. 3.3 times the length of a light year, and a light year is already very, very long, distance-wise. The real reasons, at least according to me, that you want to use scientific notation are not that at all. The real reasons are all about precision and estimation. Okay, so we use scientific notation because we want to honestly communicate precision. And we also, it turns out, it also makes doing estimates straightforward. And okay, sometimes it's convenient to write everything in meters or everything in kilometers or however we want. And yes, it's useful to write big and small numbers, but those are not, if that was all we were doing here, scientific notation and sig figs would not be worth your time, really. Let me just see what's happening in the chat. Yep, everybody's just giving severe crap. All right, let's move on. Okay, so today what I want to do is when I give you two numbers, I want you to be able to tell me which of them is more precisely given. I want you to understand how to give a measurement to a particular number of significant figures. So if I say, how tall is that building to 3 significant figures, you should be able to give me a number that has those 3 significant figures. And also I want you to be able to use scientific notation to quickly estimate the value of a difficult calculation. Okay? All right. And as I say, just interrupt me if you have any questions along the way. But let's get started. Okay, so first off, let's talk about scientific notation as being used for precision. And the way I like to think about this is not all numbers are created equal. So suppose your parents ask you to go to the shops and they say, get us a kilo of chicken breast from the deli. All right. And you go and you take the money and you go to the shops and you come home and you plonk it down on your parents' scales. And I want to know here what values that scale could read there would cause your mum or your dad to go, what the hell are you doing? Why did you get so much? Or why did you get so little? So just in the chat, can I get you to nominate what's the smallest reading we could have here on this scale? And notice it's in grams, this scale. What's the smallest reading we could have on this scale that your mum would be okay with? So I'm going to give you 20 seconds to write that in the chat. Arian's mum is very forgiving. Talil's mum wants nothing less than 1,000. 990 for Brittany, 950 from Stella, 900. So some parents are more permissive than others, but all of them, are allowing something other than exactly 1,000, except for Patrick's and Talil's. And now, can I get everyone to nominate what's the largest value that you could come home and your parents would be okay with? Given, of course, that you're spending their money and they only have this one recipe to make. Jerry's happy to bankrupt his family in the pursuit of maximal chicken. Okay. All right. Hopefully the picture that we're getting here is that when you get asked to go and grab a kilo of chicken, nobody really means by that go and get exactly 1,000.00 grams of chicken. What they mean is go to the deli, ask for a kilo of chicken, and whatever they give you, come home with it. And hopefully they'll give you something close to a kilo. Maybe a little bit more, maybe a little bit less. Maybe your parents have a preference for always getting a little bit more. Maybe your parents have a preference for not going over. But nobody expects you to come home with 1,000.00 grams of chicken. Okay, let me give you a different example now. Suppose one of your parents gives you their card and says, go to the ATM for me. And I want you to withdraw $350. Now, I know that's very trusting of them, but they're really busy. They've got this, they need to give this person $350 to fix the sink. They can't leave the house because it's overflowing. And you go out and get the money for them. They trust you with their PIN and you plonk it down on the money counter because they have a money counter. In that case, what's the lowest value that your parents are going to be okay with? What's the lowest amount of money that you could come home with in that scenario? Yes, Teresa, it's fraud, but I don't think your parents are going to press charges in this scenario. Doodles buying ice cream. And I think everybody's kind of got the picture here that if you come home with anything other than $350, then your parents aren't going to be super happy with you, unless, of course, you bought the chicken. And on the other hand, if you came home with more than $350, they might be equally unhappy because they might say, well, you just took that out of my account. I only wanted $350. So when somebody says they want $350, they mean $350. When somebody says they mean a kilo of chicken, they don't necessarily mean exactly a kilo of chicken. Okay. Oh, sorry, I forgot about this part. So there's a difference between a kilo of chicken in common language, the way English language speakers talk, and $350. 1 kilo of chicken doesn't really mean 1.00000000 kilos of chicken. It means one-ish kilos of chicken. $350 really does mean $350.00, and we don't really have any decimal cents that you can withdraw at least. So this sort of thing comes up in science all the time. Sometimes you really, really, really care about exactly how much of something you have. And sometimes you just kind of like, well, we just need some and just get that amount. So let's look at these instructions here. Take 2 beakers, and into each beaker, pour 100 mils of water. Weigh out 200 milligrams of chemical X and slowly mix it into the first beaker until dissolved. Weigh out 200 milligrams of chemical Y and mix that into the second beaker. Boil each beaker until all the water is evaporated and weigh the residue of each chemical. So in those instructions there, we've been given 4 different numbers, or four numbers. We've been given 2 beakers, 100 mils of water, 200 milligrams of chemical X, and 200 milligrams of chemical Y. And I want you to just think about, like, well, which of them really needs to be exact, and which of them does it not really matter that much, and we have a little bit of wiggle room on. So Sabir says the beaker should be exact. So that's probably true. If it says to go and get 2 beakers, it would be very strange for you to come back with 5 beakers, and it would also be very annoying if you only came back with 1. I suppose you could have, I suppose you could come back with 50 beakers, but you're only going to use 2 of them anyway, so it's a little bit of a moot point. What about the 100 mils of water? Just in the chat, say whether you think that 100 mils really needs to be exactly 100 mils. Could it be 95 mils? Could it be 110 mils? Think about what's happening to the water afterwards anyway, or what the water's being used for. Yeses and nos are not super helpful, because you might mean yes, there's some wiggle room, or you might mean yes, it needs to be precise. Okay. So Liba says the water doesn't need to be super precise. And I would agree with that, because if you think about it, the chemicals are getting dissolved in the water. So we really just need enough water to dissolve the chemicals. And then we're boiling off the water anyway. So what we're really looking for is to weigh the residues carefully, but the water's disappearing anyway, and we're not capturing it. It's just evaporating away. Right? On the other hand, those chemicals, they really do need to be quite carefully measured, because what we're going to do at the end is we're going to weigh how much is left. So if we actually only put in 170 milligrams, we might weigh at the end that we've got 170 milligrams and say none's gone missing. But if we carefully weigh out the 200 and then we get 170 later, then we can say carefully that 30 milligrams has gone missing. Hopefully that makes a little bit of sense. Can I get maybe some thumbs up, thumbs downs, go faster, go slower type stuff going on? Some ticks and some go fasters. Okay. All right. So the way we deal with this in science is we actually give these values. When we give them to you, we give them at a different level of precision. So what we would do is we would write 200.00 milligrams of chemical X. And by putting those 0.00s on there, we're making it really clear that no, we really care about that second decimal place. We really care about that first decimal place. With the 100 mils of water, we're not going to put any decimal places on this, because we're just saying 100, but you know what, if it's 99, whatever, right? And we can find a way to be even less precise about this later on once we have scientific notation. The 2 beakers, we've written it out in words, and when we write it out in words, we really mean, like, count the beakers, please, that many. Okay. All right, so here's how, went too far. So here's how we deal with this. Here's how we deal with this using scientific notation. So the way we communicate this is we use significant figures. So what we do is we imagine writing out the measurement to infinite precision. So let's say we're measuring, we want a building to be a certain height, and I'm the engineer, and I say, what I really want is for this building to be 42.1876455898812234609033467299267196027263564 meters tall. All right. And then, as a scientist, as an engineer, as a builder, you take a step back and you say, of that, I did Samir, of that, how much do I really need? Like, how much do I really need to keep of all of this? And you say, what's the first digit, if I count from the left, 1, 2, let's go down the line, where honestly it would be okay if somebody got that wrong. Right. And so we think about the scenario, we think about the measurement tools we have, we think about sort of what we're going to use this measurement for down the line. So in the previous one, we're thinking about, okay, we're going to measure chemical X later, so we better get it kind of fairly right at this point. But we only have a scale that measures to the nearest milligram, so what would be the point of going beyond that, etc. And in this case here, you'd say, well, builders, they only have measuring tapes. They only go down to the millimeter. So this is 18, that's centimeters, 187, that's millimeters, but we're never going to get that 6. We're never going to be able to measure that 6. So what would be the point in keeping it? So let's just round it away, and we'll say the building is going to be 42.188 meters tall. Okay, so that measurement there has 5 bits of information in it. The 4, the 2, the 1, the 8, and the 8. We would say it has 5 significant figures, or 5 sig figs. And that measure of 5 is really a measure of how precisely we've measured this. If we get out our laser now and we say, actually, we're going to measure this down to the nearest nanometer, maybe not nanometer, micrometer, then we can keep an extra 3 decimal places, and we'd have 8 bits of information. So we'd have something more precise. On the other hand, if we're just eyeballing this and we're an experienced builder, we might be able to look at that building and say, 42 meters. And in that case, you'd have 2 bits of information. You'd have 2 sig figs. So you'd have 2 units of precision, basically. Where is my mouse? Here it is. Okay. So in this way of thinking, you can write the same number, but if you write it with a different number of decimal places, a different number of sig figs, then you kind of mean something different. So if I say, I've got 22 minutes till this meeting, that's enough time for me to go and get a cup of tea, then I don't really mean 22 exactly minutes. I mean, like, well, I've looked at my clock. The meeting starts at 45. It's 23 now. So, it could be 21.6, it could be 22.3, but either way, it's enough time to get a cup of tea. But if I say it took 22.000 meters to run this race, there's Mo Farah there, then what I really mean is it took 22 minutes and it took it down to the millisecond. Because if I wasn't measuring down to the millisecond, I never would have bothered to give you these extra decimal places. I never would have given you a value to 5 sig figs if what I really meant was 22 minutes-ish. Okay. Hopefully that's all making sense so far. Hit me up in the chat if it's not. Okay, so where does scientific notation come in? Scientific notation is just a really convenient way to write these numbers so that the level of precision is really clear and comparable between different numbers. So in that previous example, both of them were 22, but one of them was 2.2 times 10 to the 1. That equals 22, 2.2 times 10. One of them was 2.20000 times 10 to the 1. Same number, but this one has much more precision. So once you write a number down in scientific notation, by convention, we always just put a single digit before the decimal place. Once you write it down in scientific notation with a single value before the decimal point, then its level of precision becomes really clear. All you do at that point is you just count how many digits you've got written down. Or you can reverse that logic and you can say, if I want 5 sig figs, then I'm just going to write it in scientific notation, and I'm going to stop writing when I get to the fifth thing I have to write. Okay. Okay, so the more sig figs a number has, the more precisely it's been stated. And the number of significant figures is just the number of digits you would write if you were going to write that number in scientific notation. Okay, so that's kind of the point of sig figs. It's all about precision. It's not like rounding where it's not just another type of rounding. It's really about scientists being able to communicate clearly with each other when they mean I want 2-ish of this thing versus when I want 2 of this thing. Okay. The other useful thing for scientific notation, and I would say the more useful thing, is for doing some estimating. And the reason scientific notation is really useful for estimating is because it breaks up a number into 2 bits. It gives you a sort of an exactish little bit, and then it gives you a general sense of how big the number is. So if we have 4.57 times 10 to the 12, the 4.57 just kind of tells me, oh, this is the exact number that got measured when we did the measurement. But the 10 to the 12 tells me, wow, this is a really big number. This is a million. This is a trillion, right? So this tells me if somebody tells me they have 4.57 times 10 to the something dollars, then there's a big difference between the person who has 4.57 times 10 to the $9, possibly Donald Trump, if he's to be believed, versus somebody who has 4.57 times 10 to the $3, me. But there's not that much difference between somebody who has 4.57 times 10 to the 3 and someone who has 6.5 times 10 to the 3. So most of the information here is actually in this 10 to the, and it's only kind of the little bits and pieces, details that are in the first bit, in the 4.57. So what this does is this is going to let you do estimates really quickly if what you really care about is the big picture over here. So let me show you a couple of examples of that, and then we'll be done. We'll have some time for some questions, and then I'll let you go. Okay, so let's say you know that the distance to Perth is 2,734 kilometers, and you know that a typical plane takes 3 hours and 35 minutes to complete the journey. And I want to estimate how fast it travels in meters per minute. Now that's a weird unit, but you might be thinking, oh, well, every minute, how far are we going? That's kind of I can think through that in my head, and I can have a general sense of how fast is this thing going, right? So we do our normal thing, speed equals distance over time, and we get something kind of ugly. Like, I don't know how to do this in my head. Maybe you do, but I don't. And it's really tough. You'd have to reach for a scientific calculator at this point, I would have thought. Maybe you're better at mental arithmetic than I am, but I can't do that in my head. But what I can do is I can write it in scientific notation, right? So I can say, well, this is 2.73 times 10 to the 6, because this is 2734000.00, and then I'm going to move the decimal point 6 to the left. So this is times 10 to the 6, times a million. This one here, I'd have to move the decimal point 2 to the left. So this is 2.15 times 10 to the 2. And then as soon as I look at this, well, I can see that, well, okay, let's say I don't care about the details for a moment. This is just 10 to the 6 divided by 10 to the 2. That's really easy. That's 10 to the 4, right? So even if I don't know the exact speed that the plane's going at now, I know that it's going roughly of the order of 10,000 meters every minute. And I can go, whoa, that's a long way. That's a really long way that plane is going every minute. And then if I really cared about the exact speed, then I could say, well, okay, now I'm going to do the 2.73 by 2.15. But notice even that's a lot easier now, because I could say, well, 2.7 is only a little bit bigger than 2.15. It's like 1 and a bit bigger. So we're going to get 1 point something times 10 to the 4. And what is 1 point something? That's having my answer to one significant figure. So if I just do the 2 divided by the 2, I get an answer to one significant figure. If I do the 2.7 divided by 2.1, 2.2 in this case, then I would get my answer to 2 significant figures. And if I do 2.73 divided by 2.15, then I get my answer to 3 significant figures. So you get to choose how accurately or how precisely you want your answer. You can just choose to just do the 10 to this, and then you get a ballpark estimate. We would call that the 0 significant figure result. Then, if you want it to 1 sig fig, you just round all these off to an integer, and you just do that calculation. If you want it to 2 sig figs, you do another, so on and so forth. Hopefully that makes sense. I'm just going to give you a moment to process that, and then we're going to do a slightly more complicated example. I'm not really giving you a moment to process it. My tea's just gone cold and I want to finish it. Lies, all lies. Okay. All right, so let's do one more complicated example, and then I'm going to let you go. Okay. So, it turns out, and this is just something I'm going to tell you, this top line here, that if you store a kilogram of helium gas in a sealed container, the pressure that's going to be exerting outwards on the vessel is 2.078 times 10 to the 3. And then we've got some units here. This is pascals per Kelvin meters cubed. So whatever, some unit for this constant here. And this constant is all about the properties of helium and how gases work. But the important thing is here is this is just a number multiplied by temperature divided by volume. So the idea here is the hotter this gas gets, the more pressure it will create because we're multiplying by temperature. But we're also dividing by volume. So the more tightly you compact this gas, the smaller this V gets, the bigger the pressure. So this is how we're reading this equation. It's a constant multiplied by pressure and divided by volume. Okay? So suppose we've got a vessel, so like a canister, and it's rated to handle a maximum pressure of 5.17 times 10 to the 8 pascals. And let's say this might have been done in like a quality control sort of thing. If you work in a scientific lab, any piece of equipment you get is going to come with some specifications. And so the manufacturers have given us this as the specification. And it happens to have a volume of 0.024 cubic meters. So just for some sense of reference there, that's about this big, sort of, if you imagine something yay big. Oh no, sorry, maybe more like that. And we're going to use it to store it in a regular room. It's not going to be temperature controlled, so it might get up to, in the worst case scenario, it might get up to 40 degrees Celsius, which is, in the standard units, 313 Kelvin. So let me know if this is sort of, if the problem is unclear, even if the solution is tough. Hopefully everyone can understand the problem here. We've got some relationship between temperature, volume, and pressure. We have a maximum pressure that we don't want to exceed, and we want to know, does this volume and this temperature cause us to exceed this pressure? So what we're going to do is we're going to plug in our volume and our temperature, and oh God, we're going to get some horrible, horrible maths to do. And we want to know whether all of this is bigger than this. All right, so is our vessel going to be okay? And it's not clear to me that you could do this without a scientific calculator. Well, I certainly couldn't. As it's written like this, I'd be like, oh, I don't know what to do here. But, and just by the way, this is analogous to the very last question on your worksheet this week. So when I'm looking at this, I'm thinking, oh God, what the hell do I do? All right. But we're going to use one of the neat tricks of scientific notation. Okay. So one of the neat tricks of scientific notation is that any multiplication like this can always be split up into 3 sections, or in math class 2, because they always don't write the units and it drives me crazy. But 3 sections. So there's the details. That's all the little numbers that go out the front that, to be honest, don't really matter. Then there's the big picture. The big picture is your 10 to those, so your powers of 10. And then there's your units. Okay? And the units here are, well, you just take them from, so it's pascals per Kelvin, meters cubed, times Kelvin, divided by meters cubed. And so we've kind of split this up into 3 little sections, right? And what's nice about this is then we can treat each of those little bits separately. So the details part, that's just a bunch of small numbers which are multiplying and dividing each other, but they're all going to be like, this is going to 2 times 3 divided by 2. So this is going to be like, I don't know, 3-ish, somewhere around there. But like, maybe it's 3, maybe it's 4, maybe it's 5, maybe it's 7, whatever. Like, it's just it's some number. And if you want to know it, then you can do this calculation. And if you want to know it to a particular degree of precision, then you do it with more and more significant figures. So if all we want to know is 1 sig fig, we would just go 2 times 3 divided by 2 is 3. If we wanted to know to 2 sig figs, we'd go 2.1 times 3.1 divided by 2.4. If we wanted to know it to 3 sig figs, we actually can't, because we don't have any more sig figs on the volume down here. So the most we can know is 2. That's as precise as we can ever be. Okay, but it's just some number. The units part, this bit over here, is actually really useful in science, and I would really suggest you do your calculations with units in there. The reason it's useful is because once you cancel these units out, k to the negative 1 times k is k to the 0, so it's just 1. Meters cubed divided by meters cubed, that's 3 minus 3, m to the 0, that's 1. So all we're left with is pascals times 1. Pascals is exactly what we want for pressure, so we know we've used the right formula because we know the units have come out correctly. That's more a tip for science. You don't really need that for math class, but very useful. Annoys the crap out of me that most people don't do that. But the really useful thing is in here, the big picture. We've got 10 to the 3 times 10 to the 2 divided by 10 to the negative 2. So this number here is going to be 10 to the 7, right? But we know that our vessel could take something. Let's go back to the previous slide. We know that our vessel could take values up to 5 times 10 to the 8. That's a whole order of magnitude above what we've got here. We've got our pressure is in the 10 to the 7s. Maybe it's 3 times 10 to the 7. Maybe it's 4. I haven't even bothered to do this bit, but I know it's in the 10 to the 7s. Our vessel can take something into the 10 to the 8s. So we know we're okay. We don't have to go any further with this calculation. We're done. We know this vessel is okay because we've made the estimate. And then if we want to know it more precisely, then we can just do this part of the calculation to whatever level of precision we want to. Okay, that's all from me. Does anybody, before I sort of start letting you break away, does anybody have any questions for that they want to clarify there? Does anyone want me to go back to certain slides or anything like that? No? Okay. Would anyone, so what I'll do is I might stop recording now and I'll stop sharing my screen.